Hello everyone, welcome to this revision video on rates of reaction, or kinetics. So what do we know? Well, we know that the rate of reaction is affected by a lot of different factors, and collision theory is the idea about how the impact these different factors have on the rate of reaction. And we know that a reaction can't take place unless the reactants have sufficient energy to react. So we're going to start off by thinking about how does collision theory explain why reactions take place. So what's collision theory? So collision theory is the idea or the theory that explains how reactions take place. All particles have energy, and collision theory states that the reactants will only react with each other if they collide with enough energy and in the correct way. So, what needs to happen for a reaction to take place, and why doesn't all collisions result in a reaction? Well, all particles have energy, and the amount of energy they have is dependent on the temperature, is the sort of main idea there. But we're going to have a distribution of energies within our system of particles. And collision theory is stating that the reactants need to collide with enough energy for the reaction to occur. And the chance of a collision happening is increased by increasing the concentration of the stuff that's in there, the pressure, so the number of particles in the particular volume for gases, which is very, very similar to the concentration, or the surface area of the reactant. So if there's a bigger surface area, there's more chance of collisions occurring. Now, only a small, tiny proportion of collisions are actually going to result in reactions. So for a reaction to take place, the molecules must have enough energy to come in and start breaking the bonds. And this is what we mean by, or we refer to as the activation energy. So if very few collisions are successful, then therefore very few collisions have enough energy to start the reaction. Maxwell-Boltzmann distribution. Okay, so this is a graph that shows the distribution of energy amongst the particles within a system, okay, within a gas solution, whatever it is. Some of the particles are very high energy, okay, we kind of imagine it being infinite, we don't say there's a maximum on it, but one of the key things is that no particles have zero energy. So let's go back to activation energy. What's activation energy? So activation energy is the minimum energy needed for a reaction to take place. So if you put EA, the activation energy, on a Maxwell-Boltzmann distribution, then the area under the graph to the right of the activation energy represents the number of particles with enough energy to react. So how does the temperature affect the number of molecules with energy equal to or greater than the activation energy? Well, at higher temperatures, the shape of the Maxwell-Boltzmann distribution changes. It sort of shifts to the right, and therefore the number of particles with higher energy increases. Therefore, the number of particles with equal to or greater than the activation energy also increases. So why does a small increase in temperature lead to a large increase in the rate of reaction, or a large effect on the rate of reaction? Well, the graph shows that the number of particles with enough energy to react, i.e. equal to or greater than the activation energy, increases at the higher temperature. This is because we're increasing the frequency of collisions, but also we're increasing the number of particles with equal to or greater than the activation energy. So the effect of increasing the temperature is twofold. So we're increasing the frequency of collisions. Remember, always make it time-based. It's always frequency or collisions per second or collisions per unit time. And the number of particles with equal to or greater than the activation energy. Okay, so this is why we get a big effect on increasing temperature. So how do catalysts affect the rate of reaction? Well, we kind of know that catalysts speed up reactions. We've known this from GCSE. So what do they do and how do they do it? Okay, so they increase the rate of reaction and they don't get used up in the process. Okay, so that's kind of what they do. So how do they do it? Well, what they do is they provide an alternative reaction pathway with a lower activation energy. Okay, and it's important to remember that it's an alternative reaction pathway. It's a bit like Hess's law, where you're going from a start point to an end point, but you're finding a different route. And this different route, this alternative reaction pathway, has a lower activation energy. So by giving it a lower activation energy, you've increased the proportion of particles with equal to or greater than the activation energy. And therefore, you're going to increase the probability of a successful collision or effective collision between the reactants. So to summarise these, okay, how does collision theory explain why reactions occur? So collision theory says that for a reaction to take place, the reactants must collide with sufficient energy to start breaking bonds, which is the activation energy. They also need to have the correct orientation. Okay, so if there's one end of a molecule needs to bump into a certain end of another molecule for the reaction to occur, if they bump into it the wrong end, it's not going to happen. Okay, so orientation does have an effect as well, which is why so many fewer reactions actually happen. Maxwell-Boltzmann distribution shows us how the energy is distributed amongst the particles. And on it we can look at the most probable energy, the mean energy, and also see on it the proportion of particles which have equal to or greater than the activation energy, and how that graph can change if we change factors such as temperature and so on. Catalysts will increase the rate of reaction by providing an alternative reaction pathway with a lower activation energy, increasing the proportion of particles with equal to or greater than the activation energy.